Hi, in this video we are going to talk about Quicksort algorithm, so let's get started. The good implementation can be about 2 or 3 times faster than its main competitors, the merge sort or the heap sort. It's very important that it is not stable. In efficient implementations, the relative order of equal sort items is not preserved. Quicksort can operate in place on an array, requiring small additional amounts of memory to perform the sorting. If you may recall, merge sort has a linear memory complexity. That means that it does need an additional memory space. And on the other hand, Quicksort can be implemented without any additional space, and it has a time complexity ordo n log n on average, but the worst case running time is quadratic, means ordo n squared. Pivoting is very important, and this is every sorting algorithms has advantages and disadvantages, and the main disadvantage of Quicksort is the need of pivoting, because pivoting is very important. Sometimes the leftmost element is the pivot, but it is not the best, causes worst case behavior on already sorted arrays, so usually random indexing is better as far as pivoting is considered. We are going to talk about it later at the illustration, it will be clear. And choosing the median is even better. It was invented by Professor Sidwig from Princeton University, and he came to the conclusion that pivoting is very important, okay, and what's the best pivoting strategy, and he came to the conclusion that choosing the median is the best solution in these situations. So use insertion sort, which has a smaller constant factor and is thus faster on small arrays, and that's why, as I said earlier, merge sort and quicksort has insertion sort as a sub algorithm, and quicksort's divide and conquer formulation makes it amenable to parallelization, which is quite a disadvantage. But as I said earlier, the main disadvantage of quicksort compared to merge sort is that we have to choose the pivot. Okay, so let me see the illustration. We have an unsorted array, and in this situation the pivot element will be the leftmost, but we could pick the pivot at random, but here the first element will be the pivot, and the algorithm can be easily implemented and formalized to random indexing concerning pivoting, and it's not so hard. But in this situation we are focusing on the leftmost indexing, and we choose the leftmost element to be the pivot. So in this situation the pivot is the 3, and we keep comparing the items and checking whether it's greater or larger, because we want to, the aim of this approach is to separate the array with to numbers that are greater than our pivot elements and numbers that are less than our pivot element. In this situation, the pivot element is the 3, and if we want to find an algorithm that can solve this classification problem easily, so we keep comparing it 1, we came to the situation that it's smaller than 3, so it's okay, we keep going. 4 is larger, so we mark this item. 1 is less than 3, so we swap the 1 with the 4. Then we keep going. 5 is greater than 3, so it's in the right position. Then keep going. 9 is greater than 3, so it's in the right position. But 2 is less than 3, so we have to swap it with the first marked number, which is 4. So we swap them. 6 is greater than 3. 5 is greater than 3, so it's okay. And 3 is greater or equal to, it's equal to 3, so it is in the good position. And it's very important that the last step we have to swap our pivot element with 2 in this situation. Why 2? Because 2 is the last item that is less than 3. So we swap them and consider the pivot item to be sorted. So number 3 is sorted now. And we have two subarrays, 2, 1, 1 and 5, 9, 4, 6, 5, 3. We keep call or algorithm recursively on these two subarrays. It's very powerful sorting algorithm. So we started again with 2. 2 is the leftmost element. It's going to be a pivot. As I said earlier, a better solution would be to pick a pivot at random, for example 1, or the rightmost element. It can be the pivot 2. We keep comparing it with 2. It's smaller than 2, 1 is smaller than 2. So we have to swap it with the last one. Okay. We keep going again with the 1. 1 is equal to 1. Okay. So we consider the pivot to be sorted. Because it's a single element, we consider it sorted automatically. We start with 5. 9 is greater than 5, so we mark it. 4 is less than 5, so we have to swap our element with the blue one. Okay. 6 is greater than 5, so it's okay, and we mark it. 5 is equal to 5, so we mark it. And 3, we have to swap 9 with 3. And we have to swap the pivot element with the item, the last item that's smaller than our pivot, and we consider this pivot to be sorted. Okay, we call this method recursively on the subarrays. Okay, we consider 3 sorted, we consider 4 sorted, we keep comparing 5 with 6, it's less than 6. And 9 is greater than 6, so we swap 5 with 6 and we consider 6 sorted. And that's all about Quicksort. It's a very powerful tool, and in the end all the numbers are sorted. So that's all about Quicksort. Thanks for watching.